Hello, today we're going to be talking about units of measurement and conversions. Let's start with a very quick review of the difference between a scientific theory and a scientific law. Theories in science attempt to explain whatever observation or phenomena is happening. So there's explanations of what is going on, why it is happening. Laws, on the other hand, they describe patterns of phenomena. They're just descriptions. I'll give you a good example. So let's talk about the law of conservation of mass. Conservation of mass. So law of conservation of mass means that the amount of matter, the mass, stays constant no matter what is changing in a chemical or physical change. All right, it doesn't say why the mass stays constant, just that it does stay constant. So it's a description of what is happening, but it doesn't attempt to explain anything. That's why it is a scientific law. A theory, on the other hand, would be something like kinetic molecular theory. Kinetic molecular theory explains what is going on with the molecules, the particle nature of matter, and how those molecules' movement, kinetic, so particle motion, and that different motion of those particles affects a lot of the macroscopic properties that you see of those particles. So this is an explanation of what's going on, and that's why it is a scientific theory. Now, remember that our observations can be considered qualitative or quantitative. Quantitative means there's going to have some kind of number involved, a count or a measurement of some kind. And so when we're talking about measurement in this section today, there will always be some kind of unit and number. So we have a number and a unit. And I would like you to get in the habit of not only having the actual number, the unit, but also the substance labeled as well. So a good example of that would be maybe like 15 grams of water. You have a number, a unit, and the substance being measured. It's not 100% true that you would need to label the substance, but very frequently in chemistry, that is good practice. Now we're going to be using the SI system of units. And SI stands for System International. And really it's from the French Système International. But you can remember it as the International System of Units. And you should know the SI base unit for these different quantities. The SI unit for length is the meter. And the abbreviation is M for meter. The SI unit for mass is actually the kilogram. In kg, kilograms. The SI unit for time is seconds. Use S for seconds. The SI unit for temperature is Kelvin. Although Celsius is also used really, really often, and we'll look at the difference between the two in just a few slides. Amount, this would be a count. When we count things, we use the mole, and it's abbreviated MOL, which I know isn't much of an abbreviation, but we can't use M because that's for meters. For electric current, the SI base unit is ampere, or amps for short, but we abbreviate that A. And then luminous intensity, you're not going to see a whole lot in chemistry, but we typically use the candela for that, and that's abbreviated CD. It's one of the SI base units, so I wanted to include it, but it is not something you're going to really encounter in this class. Let's quickly review the difference between weight and mass. Mass is the amount of matter. It's a measurement of the amount of matter that something contains, and it's measured in kilograms is the SI unit. Very frequently you're going to see grams being used in this class. But weight then refers to the force of gravity on an object. And we frequently use pounds for weight, but there are other units. It's not going to be super important for you to know how to measure or define weight for a chemistry class. But I did want to point out that there is a difference between weight and mass. So even if you'll hear people say like weigh the substance as like a verb, they're going to mean measure the mass of the substance. So we already talked about the SI system of units, these consistent units that we use across different fields to measure particular types of measurements. But the metric system connects those by being base 10. Okay, so when you're multiplying by multiples of 10 effectively, or dividing by multiples of 10, we can use prefixes to indicate how large or how small that measurement is. And so really common mnemonic is this like King Henry died by drinking chocolate milk. And you can use that if that works for you, but it would be kilo, hecto, deca, then your base unit, deci, centi, milli. But I want you to focus on 3 of those. So kilo, centi, and milli. So kilo means there's 1,000 times, right? It's 1,000 times bigger. Centi would be 1/100th, and milli would be 1/1000th the size. So like there are 1,000 grams in a kilogram. There are 100 centimeters in a meter. There are 1,000 milliliters in a liter. So you notice I'm adding those prefixes on to the base unit. And so these are the ones that I would like you to remember. So these are the factors that you're multiplying by from that base unit. Occasionally you'll see other ones pop up like micro or pico for chemistry. Those two come up occasionally. But I'll always give you the conversion for those. These ones you definitely need to know because they come up all the time. You need to know them for sure. Now we just talked about some of those metric prefixes and knowing the conversion there. That brings us to conversion factors. Conversion factors are fractions that equal 1, where their values are equal to 1. And I'll show you what I mean. Let's use some simple ones to start out with. So we know that there are 12 inches, let me write that on either, 12 inches in 1 foot, okay? Simple conversion. I could write that as 2 different fractions. 1 foot over 12 inches, or I could write it as 12 inches over 1 foot. But effectively, this has a value equivalent to 1, because that's the same length. We're measuring length there. So when I multiply that by a measurement, I'm not changing the actual size because they're both the same length. I'm just changing the unit that it's being measured in. And we're going to be looking at a lot of examples of this. Let's look at one more. So let's say then I wanted to do feet. There are 3 feet in 1 yard. So I could write that as 2 different fractions. I could write it as 1 yard over 3 feet, or I could write it as 3 feet over 1 yard. They're both valid conversion factors for that equality. So why are conversion factors useful? Well, they help us when we're converting units. Okay? And we're going to get into a procedure called dimensional analysis. It's just a fancy way of saying using conversion factors to convert units. And I'm going to show you a little bit of an example here. Let's say I've got, 15 yards, okay? And I want to know how many inches is that? Okay. Now, we could just figure that out mathematically, but let me show you how to do it with dimensional analysis. If I have 15 yards, okay, we already mentioned that there are 3 feet in 1 yard. And actually, let me be more consistent here. I want to just use yard is YD, yard, like that. And the reason I use this conversion factor is because there are 3 feet in 1 yard. This has a value of 1 effectively because those things are the same length. So when I multiply here, I'm changing it from yards to feet, but the actual distance being measured is not changing. And I chose to put yards on the bottom so that the yards can cancel out. So just like in math class, when you have a variable on the top and the bottom, they can cancel. You're going to do that with units. Now, what's great about using conversion factors like this is that you can string multiple conversions together. I could go ahead and do 15 times 3 is 45 and then change that to inches. Or I could just use another conversion factor. In 1 foot, there are 12 inches. And I put feet on the bottom so the feet can cancel. And whichever unit that you're looking for in your question should not be canceled out, and it should be on the top at the end of your problem. And then you're just going to go ahead and multiply across. 15 times 3 over 1, or just times 3, times 12 over 1, or just 12. And you get 540 inches as your final answer. And so these two distances are the same, you're just measured in different units. Let's look at some more examples. Okay, so now this is a metric example. Let's use conversion factors to solve for this. Whatever number they give you in the question, that's how you should start. Always start your work that way. That many grams, and then they want us to convert it to milligrams first. So in 1 gram, there are 1,000 milligrams. Remember, milli is one of those prefixes that you need to know. It means 1/1000th. So a gram has 1,000 milligrams in it. And I put the grams in the bottom so they cancel. And so in that many grams, I have 5,712 milligrams. And whatever unit I didn't cancel is the unit in your answer. Let's go ahead and go the other way. We have 5.712 grams. And now I want to find the kilograms. There are 1,000 grams in 1 kilogram. And I put grams on the bottom so the grams can cancel. And this time I'm going to divide by 1,000. So I get 0.005712 kilograms. Now, you could absolutely do this using your metric. King Henry died by drinking chocolate milk, right? And so if you start at your base unit here, and I want to go to milligrams, I'm going to move the decimal 1, 2, 3 spots. Or if I'm starting the base unit and want to get to kilo, I can move it 1, 2, 3 spots. So that works, but I want to show you pretty much always using the conversion factor method, because when we get to more complicated conversions, the dimensional analysis will always work. This will only work in limited situations. Here's another example. 3,675.0 milligrams to kilograms. Now, I don't know the actual number off the top of my head to get from milligrams to kilograms. I'd have to do that math. But I do know that there's 1,000 milligrams in 1 gram, because I know the prefix milli means 1,000th. Milligrams on the bottom. I also know that there are 1,000 grams in 1 kilogram, because I know the prefix kilo means 1,000. And so grams can cancel. So in order for me to get from milligrams to kilograms, I divide by 1,000 twice. And so I get 0.003675 kilograms. That's my final answer. So I just wanted to show you an example where you use two of those conversion factors together. All right, so let's look at units that have multiple parts to them. So miles per hour is a single unit with two parts. Meters per second is a single unit with two parts to it. When you encounter a unit like that, I want you to write it as 35 miles for every 1 hour. That's a speed. It means if you were to travel at that same speed for 1 hour, you would travel a total of 35 miles. Now, in reality, you are changing speeds quite frequently if you're driving, but let's say you're staying at this constant speed, 35 miles in 1 hour. All right. Now, let's go ahead and change the time portion first. All right. Let's change time first, because most everybody knows the amount of like minutes in an hour and seconds in a minute. So in 1 hour, you have 60 minutes. I'm going to put the 1 hour on the top, 60 minutes on the bottom. That way hours can cancel. As long as you have one on the top and one on the bottom, it doesn't matter what order they're in. If I were to stop here, I'd have miles per minute. But I need seconds as my time unit. So in 1 minute, there are 60 seconds. So minutes can cancel. So now I have seconds, which we want. And if I wanted to, I could stop there and find miles per second. But I don't want miles per second, I want meters per second. So let's use this conversion here. You don't need to memorize that. And 1 mile is equal to 1.6 kilometers, roughly. So miles can cancel because I had one on the top and one on the bottom. Also, it doesn't matter how many conversion factors away it is, right? Like, that's quite a ways away, but that's okay. As long as you have one on the top, one on the bottom, they cancel. So if I stop there, I'd have kilometers per second. But I need meters per second. There are 1,000 meters for every 1 kilometer. That's what kilo means, 1,000. So kilometers can cancel. So by setting all of this up now, I have meters on the top, seconds on the bottom, not canceled, and that's what we're looking for in our question. Meters over second, so I know I'm ready to calculate. I'm going to do 35 divided by 60, because 60 is on the bottom here, divided by 60, because 60 is on the bottom, times 1.6, because that part's on the top, times 1,000, because that part's on the top. And that is equal to, and I'm going to round here, but it's equal to 16 meters per second. 16. And so there's my final answer in meters per second. Now, this is a lot as 5 conversion factors strung together, but I wanted to give you an example using those 2-part units, and you can use as many conversion factors as you need to get to your goal unit. Last part of the section here, we're going to talk about temperature. So the Kelvin scale is the SI unit for temperature because there are no negative values. No negative numbers on the Kelvin scale. And we don't say degrees Kelvin, it's just Kelvin or kelvins. And we use capital K for Kelvin. And so what's nice about this is that absolute zero is 0 Kelvin. It is the lowest possible temperature for all intents and purposes. It is the lowest possible temperature where there is no kinetic energy, no motion of particles. 0 on the Kelvin scale is absolute 0. Okay, so that's why Kelvin is useful. There's no negative numbers. Sometimes when we're calculating with temperature, a negative value could completely throw off your calculations. So we use Kelvin as our SI unit for temperature. Now, our other units for temperature are Celsius and Fahrenheit. Celsius is useful because Celsius is based off of water. So 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius is the boiling point of water. So that makes it really useful in chemistry because so many things that we're going to be doing are water-based, water solutions. And the conversion there is really simple. Kelvin is equal to the degrees Celsius plus 273. It's actually 273.15, but we'll stick and keep it simple at 273. So because it's just a simple addition, the actual size of a Kelvin unit and the size of a Celsius unit are the same. Same size. The Kelvin scale is just shifted up so that there's no negative numbers, which is nice. Now, Fahrenheit is useful because it's based off of like the human experience of temperature, right? So when we're feeling, like 0 degrees Fahrenheit is very cold for us to be in, and 100 degrees Fahrenheit is very, very hot for us to be in. And if you go outside of that range, it's very unlikely that we're going to survive for very long. So that's why Fahrenheit is useful. I will give you the conversion here, but you do not need to memorize this. Degrees Fahrenheit is equal to degrees Celsius times 9/5. And then you add 32. But we're not going to use degrees Fahrenheit in chemistry class. But I did want to point out, yes, we use Fahrenheit for a number of different applications. You don't need to be able to use that conversion. You definitely need to be able to convert between Celsius and Kelvin, though. And so here's an example of one of our temperature conversions. Let's say, what is the temperature? 155 Kelvin expressed in degrees Celsius. So our formula, Kelvin, is equal to degrees Celsius plus 273. So you would plug this in for Kelvin. And then to get the Celsius by itself, subtract 273 from both sides. And when you do that, you get negative 118 in degrees Celsius. Very, very cold. And that would have a negative value, which could throw off your math, depending on what you're calculating, reasons why we use the Kelvin scale. But there's your final answer in degrees Celsius.